Welcome to another episode of Earth is Our Home with Professor Thomas Blaine, who's going to be talking about part two, ocean currents and gyres. Stay tuned. Hey, welcome back to another episode of Earth is Our Home. Today we're going to be talking about ocean currents and gyres with Dr. Thomas Blaine. Dr. Thomas Blaine is an associate professor with the Ohio State University Extension Program. Tom really learned a lot last time we were talking about ocean currents and gyres.
Well, it's a fascinating topic, and I know people, have heard of ocean currents. They've heard of the Gulf Stream, and they're aware that there are these rivers of water flowing through the oceans. But it was fun for me because I got to teach the principles by which these currents operate. And just remember, it's clockwise flow in the northern hemisphere and counterclockwise flow in the southern hemisphere, and that's caused by Earth's rotation, what's called the Coriolis Effect. And in a couple of episodes, by the way, I've had some questions on this, why these pull in this particular direction. So I think I'm going to do a program here in a couple of episodes on the Coriolis Effect itself, how it works. But for right now, we're talking about how these currents respond to the Coriolis Effect, and then later we will go into the Coriolis Effect itself. Today, this is our 9th episode overall, where we've discussed Earth's climate. We started off, with climate change, the climate engine. So many aspects of this that I want people to know a lot of detail about. And eventually we will get into other environmental topics, because this is Earth is Our Home, and there's all kinds of environmental topics. But because climate change is such an important issue, we've stuck with Earth's climate, and then we've got all these side issues, like in this case, ocean currents and gyres. We started that last time, and it's a complicated issue. We couldn't finish that program, and so now we're already into part 2. And here was a map we used. The thing about it is why we have to do this when we talk about global climate change and global warming is that these currents play a huge role in this heat around the planet and in cooling down places. So that's an enormous role. If you look at the Gulf Stream, look at that. It's red. Red means a warm current. Blue means a cold current. But if you look at how the Gulf Stream carries warm tropical waters from off the coast of Cuba and other places down there in the Caribbean, and of course from the Gulf of Mexico, where it gets its name, water seeps out between Florida and Cuba and joins it. And look how it goes all the way out up, and then you get the Norwegian current that goes north of the British Isles and north of Scandinavia. And notice that's still carrying some of the warmth. This plays a huge role in distributing heat. If you look at the Alaska current, you got that North Pacific current. That water's kind of cold, but it's because you can see where it comes down off California. But relative to the waters north of it, up near Alaska, it's warm. And so that moderates Alaska's climate a little bit, and Western Canada's. So these currents play an enormous role in distributing heat. If they weren't there, we would go into another ice age. And that's what I want to talk to you about today. Here's another one. And I found this one because this has the gyres label. You had said before you were familiar with ocean currents. but not so much with the term gyre. We have the major gyres in the world. Obviously, we've got the Gulf Stream flowing around. And then when it gets over to the British Isles, a portion of it breaks down. It's cooler there, goes off the coast of Spain and Portugal. It's cooler water. It loops around. Remember, it's clockwise. So there's the North Atlantic gyre. You got the North Pacific gyre, a big clockwise circle in the North Pacific Ocean, the South Pacific gyre, the South Atlantic gyre. There's the Indian Ocean gyre. And these are the 5 major ones in the world, but there are smaller ones that constitute gyres, and maybe you can spot some here on the map. One of the things we had talked about was how those circumpolar currents around Antarctica have done a lot to prevent Antarctica from warming. If you look at the warm water currents that approach Antarctica, and you can see them everywhere, look off the coast of Brazil, warm water current approaching, that red arrow approaching Antarctica. Some of that water gets through, and it turns out that that peninsula right there off the coast of Antarctica that stretches toward South America, that particular place is warming a little bit faster than the rest of Antarctica. Look at what's happening where the warm water comes off the east coast of Africa, though. There's a lot of warm water. It's been up near the equator in the Indian Ocean. Extremely warm water up there along the equator in the Indian Ocean. The 2 equatorial currents flowing from east to west. Then a portion goes down off the southeast coast of Africa. But look what happens when it approaches Antarctica. Those circumpolar currents around Antarctica are so strong that they simply don't allow that water to get there. Now, that means that Antarctica is not warming. You know, when I showed you all the map that showed that Antarctica's interior temperatures are not warming anywhere near like the Arctic temperatures. Well, they're both cut off, but Antarctica is totally cut off by water. It's an island continent. And those circumpolar currents and also the circumpolar jet, which flows right over top of them. And you asked me at one program if the currents and the jet streams were related. And yes, they certainly are. Right over top of that west wind drift, the west wind drift you see on there, right below that is the circumpolar flow going in that same direction. And then hugging the coast, we have an east wind drift. Makes it very difficult to get in. So south polar temperatures haven't changed much. Not true in the North Pole, because the North Pole's an ocean, the Arctic Ocean. And even though it is cut off from a lot of warm equatorial waters, as we've talked about, by Eurasia, North America, and Greenland, all that land does not allow the North Polar jet stream to isolate the pole the way it does in the South because of the land features. And we've talked before about how land features affect climate. They certainly affect that jet stream. The jet stream in the north, the polar jet stream in the North Pole, there's no equivalent current to the one in the South, and therefore the North Polar jet stream is just not anywhere near what the South Polar jet stream is. And you can see that Norwegian current, some of that warm water does get up there, and it does have a little bit of a moderating effect. And that's one reason why the northern polar regions have warmed more than the south.
When the Earth was first formed, we had one landmass, and then through continental drifts, because there was no landmass at the top, is that why most of the landmass sort of has gravitated toward the northern hemisphere?
Interesting you mentioned that. It's true that in this current configuration that we have of planet Earth, most of the landmass is in the northern hemisphere. That's absolutely correct. If you look at globes depicting Earth 300 million years ago, 500 million years ago, you'll notice that most of the landmass was in the southern hemisphere.
Huh, I didn't know that.
Yes, most of the landmass. If you look, most of the northern hemisphere was ocean 300, 400, 500 million years ago. The giant continents, Gondwana was a supercontinent, and Laurentia, a lot of these ancient continents, the bulk of the land was in the south, in the southern hemisphere. But the thing about it is that causes this continental drift. Every continent and every ocean that you see here is sitting on a tectonic plate. The tectonic plate is way down below the surface. The rock is molten, and therefore these plates move. And they move at about the rate that your fingernails grow. Why it is that, it's taken this shape, I have no idea. I'm not sure anybody knows. It's just the rate. 300 million years ago, northwestern Africa hit what's now the northeastern United States. There was no Atlantic Ocean. Northwest Africa pushed on the eastern United States, which prior to 300 million years ago, West Virginia was a low-lying coastal marsh. A lot of trees and vegetation. Well, they all died, and they are today's coal. They're today's coal because they got ran over by a collision between Northwest Africa and the eastern United States, which pushed land up. When two continents collide, land goes up. And they built mountains. And the mountains they built there between about 270 million years ago and 300 million years ago were the Appalachians, which at that time grew taller than the Himalayas are today. No trees anywhere near the top. Way too cold. Way too little air pressure. All right. And then about 200 million years ago, 175 million years ago, Africa backed off. So the drift backed it off, and it opened up the Atlantic. And the Atlantic's been growing ever since, and is still growing. The Atlantic Ocean is growing at about the rate at which your fingernails grow. So why are we in a configuration now where most of the land is in the northern hemisphere? Not sure I know the answer to that. Not sure anybody does, but that's where we are.
Well, just in looking at the different arrows, the different flow, just like it keeps cold water, it appears to me that the currents tend to push the continents up.
No, I understand, but that's not right. It's the other way around.
Okay.
It's the other way around. The currents
okay.
The currents respond. Obviously, when there was no Atlantic Ocean, when Africa ran into the Northeast United States and made West Virginia mountains and Pennsylvania Alleghenies and all that, there was no ocean current. What drives the continent is continental drift, plate tectonics. the fact that these continents and oceans all sit on plates that are miles deep and are separated. You got molten rock, and they turn and move like that, and then the currents respond. If you open a very large body of water, like the Atlantic Ocean is now, you get a current that flows clockwise in the north, counterclockwise in the south. So the positions of the continents dictate the currents, not the other way around. Currents have no impact on where a continent is located at all. That's caused by huge things, you know, the tectonic plates, the fire and rock, think volcanoes, earthquakes, those kind of phenomena. Even though we're in a position now where the ocean currents don't reach the poles, they play a major role in distributing heat. And so imagine that the Gulf Stream shut down. This would prevent warm ocean waters from reaching the northeastern part of North America and Western Europe. Well, scientists believe this happened once before. If you look at 13,000 years ago, we came out of the Ice Age, and orbital forcing caused that warmth between 18,000 and 13,000 years ago. The Milankovitch cycles, the change in Earth's orbit that caused the coming and going of ice ages. And look at the warming we had, about 4 degrees Celsius, that's 7 degrees Fahrenheit, between about 18,000 and 13,000 years ago. A lot of warming, but over a very long period of time. Look what happened between 13 and 11,000 years ago. We nearly went back into a new ice age. Why did that happen? That's not something that just happens for no reason. That's a huge upheaval. When people say temperatures have always changed and a lot of the temperature change is natural, well, here's an example of one. Humans didn't do that. We were around. The Native Americans were already here. They came across it about 14,000 years ago when there was a land bridge. Sea levels were lower at 14,000 years ago. When temperature was cool, you had a lot more land exposed. But look what happened between 13 and 10,000 years ago. A lot of climatologists believe that when you look at the northeastern part of North America, it's dominated by huge bodies of water, Hudson Bay, the Great Lakes. They believe that there was a giant freshwater lake with very cold water, maybe a system of lakes, but a huge lake that would have dwarfed the Great Lakes. And they believe that this water made its way into the Atlantic Ocean off the coast of Canada. When you get a lot of cold, fresh water like that coming in, it's possible to cause the salinity of the ocean to drop. In other words, the ocean's really not salt water anymore on the surface. You got this fresh water. Temperatures of the ocean plummeted, and it shut down the Gulf Stream. So look at that Gulf Stream, how much heat it transfers. It transfers heat to the northeastern part of North America, to Greenland, to the British Isles, and to Europe. They believe that if you look there at the Great Lakes, Hudson Bay, they believe that this upheaval was caused by a dam, natural dam that was holding back water that gave way, or something else allowed huge amounts of fresh, cold water to come in and shut down the Gulf Stream, the Gulf Stream. And look at that, almost put us back into another ice age. It lasted for thousands of years. We don't know exactly, if this was something that occurred over that long of a period of time, or if a couple of major events caused such a long period of very cold temperatures. Now, some people are arguing now that global warming could cause a repeat of this event. If a lot of the Arctic ice and Greenland ice melt, and that cold, fresh water, glaciers, ice on land, all these ice, these frozen objects, they're fresh water. If you freeze water, it's fresh water. And so when you thaw it out and it runs into the ocean, it changes the salinity and the temperature. And some people throw up the scenario that this could shut down the Gulf Stream, ushering in a new ice age for Northern Europe, Greenland, the North Atlantic, basically. Now, I don't believe this disaster scenario is likely. However, I do believe that with more warming, we're going to see more water, more fresh water flowing from Greenland and other areas up there into the Northern Atlantic. And it will have, there's a good chance that it will have some influence on ocean currents and will affect climate in ways that are difficult to forecast. It could usher in, while the rest of the earth is warming, okay, you know, we've talked before about global warming is not uniform. And this is one of the reasons, you know, you could have a period in which global warming occurs, but there's an area on Earth where the temperatures are declining some. And, you know, something like this happening on a smaller scale, you know, with disturbance of ocean currents affecting climate in ways that we don't even know exactly yet, is a possibility. And so I wanted to run that by you since we did talk about ocean currents and gyres. Now you know why that upheaval occurred. You can read about that, you know, about 13,000 years ago. And you can read about why some people are cautioning that we could have another stage in the Northern Atlantic. It is true that we live in a very narrow segment of Earth's history, you know, less than 100 years typically. The Phanerozoic eon has been 542 million years. And we are fortunate because all of our ancestors lived in a short sliver like we do. They experience Earth in one way, just like we do. But now we can experience the past vicariously by studying this, because really in the past 100 years or so is the first time we've ever been able to put together Earth's climate history and to talk about these things. You know, 1,000 years ago, nobody would have known what you were talking about if you began discussing the ice ages and how ice once covered, you know, North America, Europe, all these regions. Nobody would have known what you were talking about if you began discussing an era 100 million years ago where you had tropical type climates up in the very high northern temperate zones with dinosaurs and things like that. So one of the reasons I like this topic is because it allows us, it's the closest thing we're ever going to get to experience Earth in its other epochs, in its other forms. You know, when the Earth was frozen, when the Earth was a hothouse. You know, we don't see that because we live in a very narrow sliver. And so I consider our generation to be very fortunate to be able to study this and at least experience it vicariously that way.
We're talking with Dr. Thomas Blaine. He's an associate professor with the Ohio State University Extension Program. Earth is our home. Tom, thank you again, and I look forward to our next meeting.